Welcome back to the Conjecture Institute podcast. And today I'm very excited to bring you, for the first time on this podcast, a real mathematician. Many of the people that I've had on before have studied mathematics. I've studied mathematics. All the physics graduates study mathematics. But no one is a pure, if you like, mathematician. Although, as we're going to learn today, Paul Raymond-Robichaud, who is going to tell me how to pronounce his name properly in just a moment, is in fact more properly described as an actual proper mathematician. Welcome, Paul.
Thanks for having me, Brett. I pronounce my name as Paul Raymond-Robichaud. Of course, that's the French pronunciation, and I myself I'm not too sure how to pronounce it in English, so I don't mind at all if you miss, because I would miss too.
I'm just going to stick with Paul for the remainder of this. Paul, it's great to have you here, as I say, to learn some more about mathematics. I know very little about mathematics, even though I was, and we're going to get to this as well, forced to take the 13 years worth of it at high school, forced to take another 4 or 5 years when I was at university doing undergraduate physics, but I am nothing but a novice. Tell us, how did you get interested in mathematics, and what has brought you to this point where actually you're bridging the gap really between mathematics and physics, something that many famous physicists over time, such as, let's say, Feynman, for example, have managed to also straddle this divide?
So that's going to be a very long answer, I think. My interest in math, as far as I recall, when I was a little kid, I was already into math. So I don't even know when it started, because I liked math when I was 6 or 7. I remember being a little kid, like 7 or 8, and programming the computer to compute a series that would converge toward pi, or working on quadratic equations, or doing things that I think I was a bit precocious for math. But of course, I had years of horrid school where all passion is being crushed, and so I was also interested in physics and philosophy. And I didn't start in mathematics. I started in physics and philosophy, but because I had a very bad math course in high school, like you did, and very bad math course in college. And to some extent, I don't blame the teachers. They had to follow a dreadful curriculum that was full of recipes that you have to follow. And my vision of math was that if that's what you do at the university, that's so horrid. I don't want to live through that again. But then I started physics and philosophy, and I thought it would be better, more about ideas, but it was not much better. The physics course were more about here's a wave and compute its amplitude, or something like that, and the philosophy course were history of philosophy without any kind of attempt to try to understand things. So my real passion was still math, but I had this vision of the academy that was rather negative and proven negative over and over. So after going in physics and philosophy, I switched back to math at some point, and it went really well. The university was very nice with me, and I had the courses. I think math is in better shape than physics and philosophy at the moment, but it's slowly in decline in the academic world. When I was doing my bachelor in mathematics, I wanted to understand some mathematics at the deepest level possible. I really, really liked math, and that led me to the foundation of mathematics. So I thought I would be a pure mathematician, doing pure research in pure mathematics. And what happened is I realized I wanted to understand the nature of mathematics itself, and that led me to the theory of computability. So I started to be very interested in how computation works. But the goal of understanding the theory of computation was to understand mathematics, because math is at the formal level symbols that you can manipulate with rules, and you can build a theory of mathematics about mathematics, and you can use the theory of computation to understand these theories. And at that point, yes, I had a slight interest in physics, but not as much as math and computation. But I really wanted to understand the foundation of math. And I had taken a course with Gilles Brassard, who is the inventor of quantum teleportation, and of one of the first protocol of quantum cryptography, BB84, and I really liked the course in theoretical computer science with him. And the math department where I was would not be a place where I could do research in foundation of mathematics. It was getting slowly an applied course, and I was getting more and more into the theory of computation. And he was giving a course in quantum computing, and I was immediately interested because at some point you realize that computation is about physics, that the theory of computation cannot be understood without understanding theories about physics. So I went from math to foundation of math to computing to foundation of physics and quantum theory, because I wanted to understand computing, which would allow me to understand mathematics, which would enable me to understand mathematics. So that was a very long way, but I'm like that. I want to understand things at their deepest level always. And so once I got into physics, I realized that I could do stuff because I understood math very well and the foundation of math really well, and that what was needed in the field was to give a solid foundation to many of the ideas that were puzzling people. So yeah, that's the answer.
That is something that does, I think, puzzle people generally, but perhaps even is still controversial among mathematicians, as you would know better than I do. After all, David Deutsch often refers to mathematical proof as not being an abstract thing, because a proof is a kind of computation. A computation is done by a computer is a physical thing made of matter obeying the laws of physics, and so therefore all proofs ultimately are the outworking, a fallible outworking of some kind of device made of matter obeying the laws of physics. And yet there is still this pervasive misconception that mathematics can reach some sort of abstract Platonic truth. So could you tell me a little bit more about that? Am I right to think this is still a controversial thesis within mathematics itself, that in fact there is a kind of mathematician's misconception, as what David Deutsch has talked about it as?
If you were in mathematics itself, you would never even hear these questions. It would not really be discussed that mathematics has a physical nature. That's not realized much by mathematicians. That's not discussed much. And in some sense, to do mathematics, you don't need to think about these issues. But if you want to make a breakthrough in understanding what is a proof at the philosophical level, or even at a breakthrough that would allow you to use physics to understand things, that's completely necessary. So, for instance, in my quantum computing course, I was introduced to the notion of a quantum proof. So, a quantum proof is a way to prove a mathematical statement using quantum computation. And you can prove using normal proof theory that the quantum proof does what it's supposed to do.
Yeah, so tell me a little bit then about this domain of the foundation of mathematics, because I think that, well, anyone who's read popular science, the work of Paul Davies, or indeed there's chapters within David Deutsch's books as well that touch on this. Early last century, we had Russell and Whitehead writing the Principia Mathematica, an attempt to put on a firm foundation all of mathematics, to axiomatize all of mathematics, and therefore would turn mathematics into a kind of calculation exercise. You just put your problem into the computer, it would look up the relevant, the axioms, the completed axioms, and then you would get your solution out the end of that. That was a failed project, failed and proved to have been a failed project by Gödel via one avenue, and I think Turing by another. So what therefore is the point of this foundations of mathematics domain of inquiry, if indeed we know that we cannot axiomatize all of mathematics and have a firm foundation for all of mathematics to write the next, Principia Mathematica number 2, where we actually succeed in doing that, finding the foundations of mathematics?
So part of the error in trying to have a firm foundation of mathematics is that, like any other topics, it is a conjecture that our axioms are consistent. We can't ever know, and that's something that has been seen first as a great tragedy by the people at the time, because they were really hoping that one day we could have a list of axioms that is complete and allow us to forever be certain that we'll be right. But the thing is that even the most basic statement in mathematics are fundamentally uncertain, and that's the approach that Popper and Deutsch brought to that. Even so, if we cannot be certain of the foundation of mathematics, that's not tragic. what can happen is that if our system is contradictory, we can find mistake and try to solve them, and that's what happened in the crisis of mathematics. So Russell paradox didn't lead to the destruction of mathematics. It led to some change in the axioms of set theory. At the time in naive set theory, you had the idea that from any predicate you could construct a set. That leads to the ability to construct the set of all sets that don't contain themselves, and that set can be shown to be self-contradictory. And this just showed that or initiate initial ideas incorrect, and that we have to revise them. But it didn't destroy the edifice. It just led to a very small change to say that a predicate can describe a set as long as predicate is included in another set. We had a replacement of an axiom to a theory that is now even more interesting, and that's how you should think about axioms in mathematics. They're conjecture. They're conjecture that can be refuted when we find a contradiction, and we'll never know if our axioms are correct. But what we do know is that they can solve problems. And also there's another problem in mathematics, is that the set of axioms we'll need is going to be forever infinite in scope. No system of axioms that is finite is enough to capture even the truth of basic arithmetic, and certainly not of set theory. And to some extent, that's really great, because that means that there's going to be forever stuff to do for mathematicians.
So then tell me, because we have this notion that there is this hierarchy of knowledge, and David Deutsch talks about this in The Fabric of Reality, where he says people have this idea in their mind that mathematics is about absolutely certain truth, whereas science is about not certain truth, but theories you can have high confidence in that are kind of close to the truth. And then, of course, we move to philosophy and epistemology, and there it's just whatever your favorite opinion happens to be. Everyone has their own taste about what is the best philosophical theory or what is the best moral theory. Now, then he goes on to explain, just as you have, that in fact, mathematics also consists of conjectural knowledge, and therefore, in a deep sense, is similar to things like science, things like philosophy, all of which are conjectural explanations about the world. And you've just said there that even the axioms are themselves conjectures. So if that's all true, and it's all just conjectures, in what sense is mathematics special then? What's mathematics about that sets it apart from physics?
The big difference is how you test your conjecture. In physics, you will have to do some sort of things or realize in the real world outside of your head that your conjecture is wrong. Well, if you're a mathematician, you can test them in your head. You don't need to go to the outside world. If I'm just in a room, in a prison, where I have bread and water and enough paper and pen, I can do mathematics. That's what sets mathematics apart. It's not its certainty, it's the method by which we refute conjectures.
And perhaps we could also say the subject matter itself. The subject matter itself is abstractions. It is the abstract world of numbers, of sets, of shapes, and that kind of thing.
Yes, I would describe mathematics as being about theories, not what the theories are about, but about their structure. Math is what can tell you the consequence of any theory, and can go extremely far in the consequences in a way that natural language is not as able to deal with these issues, because in natural language, terms can have a multiplicity of meaning. The sentence can be slightly ambiguous, while in math you remove this ambiguity. And the way I see it, mathematics is about abstract theories and consequences of these theories, and it gives you tools to be able to think about these theories without even, but in a way that is detached from the interpretations of the theories. It doesn't tell you how to interpret the theories.
And yet we have this claim, which is often repeated, originally put forth by Eugene Wigner, about this supposed problem about the unreasonable effectiveness of mathematics and the natural sciences. What can you tell us about that? Why should the physical universe be amenable to the tools of mathematics, which are about abstractions?
That's an extremely deep question. It's similar to asking, why is the universe governed by regularity? And don't think I have an answer to that question. What is certain is that if any kind of thing is governed by regularity, math will be unreasonably effective at dealing with it.
Yes.
Then we're asking, why is the universe governed by regularities? Why does it make sense? Why can we do this? I don't know, unfortunately.
We're going to come back to your research a little more, but let's talk some more about how it is that you personally found joy in mathematics, because it sounds like you did go through a standard school curriculum, which anyone watching this or listening to this will know is, unless you are already in a mind of enjoying mathematics for whatever reason, for the overwhelming majority of people, they find it boring. They go to the arithmetic class, then they go to the geometry class, and then the algebra class, and if they go high enough, they go to the calculus class, and so on it goes through these standard courses, often where you have to do, and they literally call them exercises to emphasize the tedium of what is actually done inside of these lessons, where, people are punished for the errors and rewarded for getting the correct answer and this kind of thing. So you survived this. How is it that, firstly, you were able to find joy in mathematics despite the fact that it was boring at school? And what do you think is a better way to go rather than what is happening at the moment?
So of course, I suffered at school like anyone else, but it got better at the university level. Even if you're coerced, at least it was more interesting. It was less about following recipe and just doing exercise very tediously. There was understanding and there was beauty in it. And even if it was, even if I had exams. I think mathematics is at the worst when you're in primary school, where they strip it of explanation. It's all about following your recipe, and even in high school or low-level college, it's all about that. But at some point, it stopped being as dreadful, even if you maintain the coercion, which is another aspect which is terrible on its own. Once it becomes more explanatory, it's easier to find joy. And when I was at university during my bachelor, there was a professor. His name was Gert Sabidusi, and I started visiting him every week, and he would show me mathematics, and we would discuss mathematical proof, and he would ask me things like, where did you use this hypothesis, or we would make comment about what other way we could have proved something. It became much more explanatory and much more fun to do. Despite still being the school system, that was something that I did with them for fun, and I was also reading books for fun. But I have to say, when I was at university, it was still stressful for me to do the course, the exams, because the amount of material is way too high. And it's only after I was done with all courses that I could devote myself more fully to mathematics with the greatest joy. And the answer to how we could learn mathematics, after many years of thinking about the topic, I found only two components. The first component is freedom, and freedom is the best way to learn anything, really. It's the answer to all questions. The questions of how often you should read a book in math is how often as you like. Whether you should do exercise or not. It's do you want to do the exercise? The answer to all questions is freedom. And every time you see a study on learning, often they don't have the freedom component. So the result is that you obtain a nonsensical answer to the questions that I've just enumerated. And freedom is the best way to go, because generally when you want to do mathematics, you have a problem in mind, and the way to solve it cannot be through methods that are predetermined. That's not how you solve problems. So that's the first component, and this doesn't lead to a single method. There's a plethora of them. For instance, these days you can use AI to understand stuff that you want to understand. And the second component is not as important as freedom, but I still find it very useful. I use spaced repetition to memorize mathematical proof, but the goal is just to maintain knowledge that you've already learned in your head. But the first, most important thing is just to read stuff you care about, think out problems you care about, and there's not a single method. I can discuss with people, I can read a PDF, I can use AI, then I can take a long walk where I ponder for hours on a problem, and there's no recipe. And that's something that all children know instinctively because they just play without any expectation. But we live in an era where people are convinced that what I said cannot happen, that you cannot learn on your own, that you need to be coerced and forced, and the result is terrible. It removes people from solving fundamental problems and try to turn them into a factory robot that receive a problem as an entry, follow a specific method, and return a solution. There's nothing great that can be done by that, and we are at an era where machines can do that for mathematics. There's no more need for humans to do that anyway.
A friend of mine, when I explained to him the ideas about non-coercive learning, he's very intelligent. He understood what I was saying, and he did very well at school himself and did very well at mathematics. But his response to me on all of this was, I wish my parents had have been more coercive. I wish they had have forced me to go to additional tutorial lessons after school and do more homework. It's weird how people's minds are that deeply affected that not only have they taken on board this idea that the only way to learn things like mathematics, for example, is via coercion, but they actually now, in retrospect, think that they would have somehow benefited from even more coercion, that the amount that they had simply wasn't enough. It's a very strange way of thinking. However, it is still the main way that almost all parents think of when they think about their own children doing well at school. Mathematics is often the number one subject held aloft as this is an indication of how intelligent you are. If you fail mathematics at school, then you are almost a failure at life, basically. I think things are changing a little bit. But let's think that we're talking to a parent who wants to try to change their ideas with respect to how they're teaching their children. Now, maybe they're not going to come all the way with us. They're not going to come all the way and say, okay, I'm not going to force them to go to mathematics class. They may still well do that. And let's say we want to make it a little bit more fun for the child. Can you tell me a bit more about spaced repetition on the one hand? And do you think the idea of a friendly tutor or a friendly mentor, which it sounds like you had at university, could also be a way of at least reducing the coercion? I think some people just refuse to give up the coercion when it comes to mathematics in particular, but at least we could reduce it a little bit.
So, a friendly tutor is very different from coercion. It's something I went voluntarily to have these lessons with that professor, so it doesn't count at all. It means that if we're doing a proof, if I'm like, I don't like this theorem, can we do another one? A friendly tutor has to say yes. He cannot force you to do anything. It's like having a friend that know more than you. It's a great thing. I do encourage, if you're a child, if you're a parent and want to give lesson to and say, maybe to the parent, I would say, okay, I get that maybe you want some structure or something like that. The only component that I oppose is the coercion component. Maybe that person you discuss, maybe you would have been happy if his parent had brought him to a friendly tutor that is non-coercive, and that he would have wished his parent had done more. The two things can coexist. The fact that you would wish your parents had displayed more care into your well-being, that they had put you in, a math camp. I remember when I was in college, I went to a math camp. All the lectures were fully voluntary, and we had lecture about all kind of topics. I still remember them fondly. So that was instruction. The difference is that there was no exam. We didn't have to go to a lecture if we didn't want to, and that was paradise. Maybe that child, we could have told him, okay, you want structure, no problem. I'm not opposed to it. Maybe go to you could have put that child into a math camp as long as it's voluntary. And enjoyable, and you will realize that the mood is extremely different. There's no stress. There's just joy, and also the lectures were more paced in the sense it was just 2 or 3 hours in the morning, and then we had more like social activities, like going to a science museum, and so that's what I would say to a parent that say, oh, I don't want my child to just do what he wants all day. Maybe if or maybe the child doesn't want that. As soon as you remove coercion, everything becomes good because by definition you would just switch if you don't like the activity. I don't oppose tutoring. I don't oppose even a thing that would resemble a university where you would go to lectures. The only thing I oppose is this attempt to force people to be into a room where you're told that you have to listen to this problem and that you will fail at life if you don't solve that. That's the source of all stress. As for space repetition, to me it is it's a technique, but one that is secondary to freedom. And a lot of people these days it's a technique where you create flashcards. I could go into details about ideas that you care about. And there's a big difference between the way most people use them. Generally, it's to pass exams, and the exams they're of course very coercive. They have time limits. They have you can't go into the deepest idea possible with them, and the result is that you have two usage of space repetition that are night and day. There's a difference between using them for an exam, where you will put things that you don't choose, that you might not care about, not necessarily formulated in the best way possible. Then you're going to memorize these flashcards for a few months, and then after your exam is done, you do after the cramming, you do the dumping. You delete all these cards because the only point of that was to pass your exam. And when I started space repetition, it was 10 years ago, I had done all my courses, and that was the period of my life where I had so much fun because I had a lot of freedom and a lot of free time to do whatever I wanted. I was starting the research phase of the PhD, so I read a lot of books unrelated to mathematics, and some were on learning, and that's where I learned about space repetition, and it really clicked for me. But what I was doing with it is put things that I wanted to think about in my own words, problems related to the things I care about in mathematics, and only such things, only things that I care about that I want to remember. And I kept adding flashcards, but the great thing it does is it enables you to retain a lot of material, but if it's stuff you don't care about, it's going to be torture. If it's stuff you care about, it's going to be paradise. So it's the primary method that I use to retain the ideas in maths that I care about, because there's so many of them. And the way I use it is just that, let's say I learn a theorem or something like that. I try to enter it there and memorize it step by step and decompose it into sub-theorems. Also, every time I learn a theorem and I find a way to improve it or to make it more abstract or connect it to new ideas, I do so. Yeah, the key is freedom for almost every method of learning.
Yeah, it's a matter of finding the thing fun first. And if you find the thing fun first, you do not need to be coerced into it. On the flip side, if you are coerced into it and the only reason that you're doing it is because you're being forced into doing this thing, then you're not going to find it fun. And so therefore you're going to find it difficult, you're going to resist, and you're not going to enjoy it at all. It's like, I used to think of mathematics at times as kind of like, I used to like mountain bike riding as well. I would still do. But if you have a large like mountain to climb, literally on your mountain bike, then if you were forced to go on the mountain bike up this particular hill, you would hate every single moment of it. However, for many people who enjoy mountain bike riding, the challenge of making progress along this mountain bike ride to the peak, you can see where the peak is, you see where you need to go, and you will make some effort to get there. And in fact, once you get there, then there's the downhill climb on the other side. Mathematics can be like this. It can be the fun challenge. You can see what the thing that you need to prove. You can see different paths that you might want to take, for example, and it is fun to you. It's the problem that you want to solve. But if someone just foists the problem onto you, then of course you're not going to find it fun, because everyone is going to resist the thing when they think there's something better they could be doing with their time. So the teachers and the parents and the educational system has devised a machine for almost inculcating people with the notion that mathematics simply isn't fun. After all, if it was fun, then it wouldn't need to be compulsory.
Yeah, and of course that's the bad logic. It if it would not be compulsory, it would be fun, and there's many other problems to that approach. It's terrible for people who would prefer to do other things, and for people who would like to do maths. We both suffer for a different reason. The people who don't like mathematics, particularly, first they're not going to use it later in their life, and I realize sometimes that. When a topic was not my main interest, it can become fun when you want to solve a problem related to that field. Let's say you have a medical problem. You would not like to learn biology perhaps in your spare time in general, but if you want to learn about the medical problem you have, you don't need to be forced, and you might even find the topic fun, even if your problem itself is very annoying. While in the case of in the case of mathematics, there are two categories of people: those who would like to do something else, and it's already torture for them. The moment they will need mathematics, they will be able to become interested. The moment that they realize, oh, my problems requires to use some mathematics, and I'm not forced to use it, they're going to be willing to use math, and they would even be more willing to do so if they had not been previously tortured with forced mathematics. And then the people like me would like math. Well, what I like is to solve the problems I care about. I don't want to be coarse. I really hate it. And I think I was quite rebellious in high school, especially toward the math teacher, because let's say I'm trying to develop a new method to your problem. The teacher would try to punish me for that, to say, no, we're doing that, Paul. And I'm like, no, I want to do this, and I'm going to do it. Sorry. That led to me being quite rebellious.
And this may intersect also with one of your other interests, which is Stoicism. Can you tell us a little bit about perhaps how this plays into your approach to learning, perhaps to mathematics, perhaps to life just in general? What's the intersection there? And also with the work of David Deutsch as well. You've found some parallels, perhaps.
I found a lot of parallel between David Deutsch idea and Stoicism. I'm going to start with the parallels, and then I'm going to show where it differs a bit. So the Stoics were some of the first who said that, for instance, the reason moral values are good, first they would view moral values and virtue as a form of knowledge that should be in the mind of the person and that lead to good actions. But the important aspect is the fact that it's knowledge inside you. So that's very similar to David's approach. And they would say that what is good or bad comes from physis, nature, rather than convention, nomos. I already think that's a better argument than about 99.9% of what you will find in the modern academic world. And they also say things like that the universe is rational, and rational means several things. It means, among other things, that a rational being like me can understand it. They have a triple notion of rationality. So rationality is the same word for all these things. It's logos in ancient Greek, and rationality. The rationality of the universe is the fact that it's well organized in a way that, among other things, lead to the possibility of knowledge and the possibility of the flourishing of virtue and the possibility of the flourishing of the system of rational beings. And then there's the rationality in humans. And the Stoic give a very special place to humans. They're special because they have rationality, and that alone set them apart from all other creatures. And that alone means that they're able to make moral choices and to either align themselves with the order of the universe that decide what is good or bad, or to reject it. And for them, virtue is purely epistemic. Vice is a form of ignorance that has to be improved by receiving the knowledge. So they're not Popperian in the sense that they don't get it's a conjecture and all that, but they have this notion of virtue and vice that is purely epistemic or psychological. And then the last rationality is the rationality in the language. So I said there was three kinds of rationality. The first is in the universe, then it's in our mind, and then it's in language. And this rationality in language and argument allow us to humans that have rationality to understand the rationality of the universe and align ourselves with it. And then they have a deterministic physics where everything is part of the universe causal chain of effects. So as you can see already, there's a lot of parallels with David ideas. The only two lack of parallel is that they would believe the universe is purposeful, it's organized in a way which is kind of intelligent, because at the time they had no theory of universal evolution. They had no theory of how complexity can emerge from more basic level units, which when you don't have that, it's very easy to imagine that the reason there's an order in the universe, that the reason humans are able to create an harmonious society is because the universe itself is organized. Oh, I have to give another example where I think they're very close to David's thoughts. It's about how humans start. So at the time, the Stoic opposite school was the Epicureans, who believed that all we care about was to maximize pleasure and avoid pain. And the reason you're virtuous is because by being virtuous, you will maximize your pleasure and avoid pain. The reason you should have a friend is again that. And they opposed that, and they had a very different starting theory of psychology. So for the Epicureans, all you want is fundamentally create pleasure, desire, maximize your pleasure, avoid pain, which is very similar to some modern bad ideas of today. Well, for them, you start with some instinct, but you have a rational faculty which is completely able to override any instinct you started with, so that you might be able to endure pain because you discover that something is virtuous. So that's the fact that we are completely rational goes against about everything you will read in modern psychology that claim that we are under the thrall of rational urges. But for the Stoics, the reason you have urges is because your theory point toward that being the best thing. And if you're wrong, if you're being vicious, it's because you're ignorant. And if you're ignorant, the method to correct it is by correcting your knowledge. And ultimately, you can tend toward this state of being a sage, where a stage, it's not something you can reach. It's something that we can forever approximate more and more by correcting these errors.
So for the Stoics, if they had this conception of a teleology in the universe where things are deterministic, and yet at the same time, they also thought that humans were improvable by a method of some kind of error correction, they could choose to be the sage if they so wished. Does this leave a place for them for free will?
So the notion of free will, they have something called the lazy argument. The universe is completely deterministic. It doesn't have free will in the sense that you could do something else, but the explanation of why we do things is because of our ideas. And you have a choice in the sense that you have a rational faculty that makes decisions, even if all these decisions are determined by the universe. So even I don't think there is free will, but there's the notion of choice. That might seem a bit paradoxical, but I think that's the best way to describe it.
So I think, yeah, do you personally, Paul, you reject a libertarian notion of free will, so-called, this idea that free will in some way might be supernatural. It would violate the laws of physics, for example.
Yes, and the Stoics would reject that too. So the universe, as we understand it, follow laws that are very deterministic, but it still has other features. It has features like counterfactuality. We can think about what would have happened had things been different. And the laws of physics, even if they're deterministic, allow to give these answers, this kind of counterfactuality. And so when we discuss about choice, it has to be also about the ideas, and the fact that what we're doing when we're making a decision, it's that we have ideas, and if the ideas were otherwise, we would have done something else.
Yeah, I like to often refer to just the notion of creativity, invoking the notion of explanatory creativity at this point, which is the thing that separates us as human beings or as people from all the other entities in the universe. And the creation of knowledge is the thing that increases the repertoire of choices before us. And you can call all of that free will or not call that free will, but it is an a unique thing that we possess. And none of it needs to say that we somehow can step outside of the laws of physics. The laws of physics just allow for the creation of knowledge, and the creation of knowledge is, in a sense, determined by the laws of physics. You know, it must obey the laws of physics, that process, but it doesn't mean that it's predictable ahead of time. And it's the inherent unpredictability of human action and human choice that makes us unique. Whether you want to label that free will or not, I think it just comes down to a matter of taste with respect to the words that we're using.
I would agree. I want to answer a bit more your question of Stoicism, because I just answered what were the parallel between the Stoics and Deutsch, and I thought they were very strong. So when you have strong parallel, often it means you can use both of the ideas together as long as there's no contradiction. And what I think the Stoics are very strong at is connecting ideas related to physics, to ideas of how we should live as human being, and they're also strong in the practices. So in a lot of modern Stoic book, you will notice that they pay attention almost only exclusively to the practice without attempting to correct it to the physics, because modern Stoic book will tell you, of course, the Stoics said that we were fully rational, but they were wrong because we're ruled by urges. And of course, the Stoics believe that what is good is determined by nature, not by convention, but it's all convention. And they said humans are special because of their reason, but of course, humans are just evolved monkeys, and they cannot have any special emerging property. And I think that the interesting thing to do is to, if you study Stoicism, is to be interested in both the practice that are about finding inner tranquility and peace of mind, but it has to be connected to deeper ideas on physics, because what the Stoics noticed is that everything was connected: physics, morality, epistemology, and that's something that's very Deutschian too, that when you want to solve a problem, there's no strict boundary between these disciplines. What you have is problems, and what you need to understand a problem related to your peace of mind might well be related to physics, might well be related to epistemology, might well be related to these things. So they would study all these things together, and that's something that has been lost by a lot of modern academics, where they're specialists because they are part of a university that creates specialists and that prevent and even punish any kind of boundary breaking. And you need a man like David to be who exists outside of the university structure to be able to walk outside of these boundaries. But it used to be the case. So Stoicism also gave me a sense of history, where I can realize that there used to be a civilization that didn't have such boundaries and that were able to make incredible progress. So ancient Athens is such a small population for the amount of thinkers that existed with issues that are still relevant today.
One of my favorite quotes from the beginning of Infinity is where David, through the voice of Hermes, or is it, I can't remember anyway, the quote is, "Do not destroy the means of error correction," which simultaneously is a moral claim, do not do this thing, and the means of error correction is a part of epistemology. And so it's about what kind of knowledge we might want to consider is moral knowledge, okay, and how we can come up with conjectures about what moral principles are. Now, knowledge itself, there must be ultimately laws of physics about what knowledge is possible to create and what knowledge is not possible to create. And so therefore you have the boundary broken down between physics, epistemology, and morality, something I don't think modern academics tend even to broach the topic. They stay within their silos and they don't want to think about connections outside. But I think we have a very strong hint through that idea, which may be very a constructive theoretic idea about what kind of moral things are possible to do in the future and what might be closed to us in the future, just via this intersection between epistemology and morality and physics, by saying do not destroy the means of error correction. I think that's a brilliant insight by David there.
Yes. For me, that was amazing to see how morality could be related to physics, and ultimately it has to be contingent on physics. I think that that's an amazing thing by David, that he's able to find fundamental solutions by not being afraid to go outside of his discipline, and that's something that I enjoy doing too if I can. I noticed that physics would need math, something that seems trivial, but that physicists don't seem to realize.
Well, now that I've got you, I've got a real life mathematician here. Something that I often talk about is this idea that Feynman had, and Feynman gave that wonderful lecture, which is available online, about mathematicians and physicists. And towards the end of that lecture, he talks about the complexity of the mathematical complexity of the laws of physics, what is supposed to be the mathematical complexity of the laws of physics. And I hear people, for example, like Neil deGrasse Tyson, the astrophysicist, but he's not the only one, there's just one name that I can think of, who say things like, perhaps the laws of physics ultimately, the successor theory to quantum theory, whatever it happens to be, is going to be so mathematically sophisticated that the human mind will not be able to understand it. It will be too complicated for us, because there seems to be this history in the history of physics where we go from an algebraic way of expressing the laws of physics through to use of calculus by Newton and Leibniz, and then you move on to pencil calculus on manifolds, and you move on to higher topology, and it seems to be getting more and more complicated. And of course, string theory is something that very few people understand, but it seems that there is this trajectory of more and more mathematical complexity. But Richard Feynman says in that lecture, perhaps the laws of physics will be more akin to the rules of the checkerboard than to something mathematically sophisticated. He said he didn't know, he wasn't coming down on either side, but he said there's no reason to think this. And we're bringing in David Deutsch and constructor theory. It seems as if the mathematics of the possible versus impossible may in fact be simple. Do you have any thoughts about this? Is there any indication that we need to necessarily become more mathematically sophisticated as we increase our understanding of the laws of physics?
So I do think we'll need to become more mathematically sophisticated, but I'm not pessimistic about our ability to do so. For instance, I said that in the beginning, the axioms of set theory, there's going to be a need of an infinite amount of them. And you might think that our brains are finite. That's the case, but nothing prevents us from eventually developing bigger brain. But we're very far from that. We're very far from needing bigger brain to understand ideas. So far, we've been able to understand all the ideas that we need. The kind of size of an axiom of math that is too large for a human brain has to be extremely enormous, or the same for any ideas that might exist that is too large for a brain. So an argument I can make is the human brain can hold a finite amount of information. At some point, there's stuff that doesn't fit. But I've been using space repetition for years, and I know one thing, that I will die before my brain has no more space, and that's just the way human memory works. The limitation that we'll need an infinitely large structure, given that we have a finite brain, doesn't imply that we won't be able to understand it. It implies that what is human, or what is a person, will need to forever be updated to something a bit larger. But the way ideas operate themselves in mathematics, it's never something inscrutable or incomprehensible. Mathematics at its basic, so the basic law of mathematics, if you will, are extremely simple. The way we use the laws of logic, we have a system for that. It's stuff like if A implies B and B implies C, then A implies C, and there's like a dozen of them. You could have more or you could have less, but they're so simple that you can use them. Or it's like how computation work at the fundamental level. A Turing machine, just look at, is this a 0 or 1 in front of me, and in what state am I, and that tell me whether I have to move left, right, or change the thing in front of me. And there's nothing fundamentally incomprehensible. All that could happen is that it's large and that our brain cannot deal with something large, but it would not be a different kind of thing. It would just be a larger thing.
And you could, in principle, perhaps, I don't know if this is an analogous situation, but look up that bit of knowledge that you think might help you to solve your problem later on. It could be written down somewhere. You might have forgotten it, or you might never have learned it. For example, you might understand the general idea about how integration works, for example, and you understand how the table of standard integrals is actually developed. But if you're performing a particular integration, maybe you don't want to start from first principles in order to get to this integral. So instead, you just look up some standard integral and then you solve your problem that way. But in principle, you could always look up the thing that isn't actually stored inside your mind at the moment. So you can make progress without knowing absolutely everything down to the bare basics.
That's true, but the argument I was making was more that there might be ideas that are even too large for that.
Yes. And so therefore, in the distant future, as you say, we will change our ideas about what a person is and upgrade the hardware, if you like.
Yes, because right now I do agree with you that you don't need to contain everything about the knowledge around you to be able to understand things. You can look up stuff and you can build a basic model, but you still need to be able to hold the basic model in your head as you solve that problem. So you still need that property that it has the basic model of looking at the table. You need to have a basic understanding of what the integral is and all that. I just think at some point we need much more bigger things or much more performant brain, but that doesn't change what we are fundamentally. It just means it's a brain with more space that will operate in the same principle.
Now, back on the July the 22nd, so a little while ago now, David Deutsch tweeted out about you, Paul, and he said, Paul is the leading master of the art of ruling out bad explanations mathematically. And because you are a proponent also of Everettian quantum theory. Now, I don't know if we can go into it in the podcast here, but can you give us a hint about how one would go about using mathematics to rule out bad interpretations of, let's say, quantum theory?
So a big problem is that we're told that there is math and there's the interpretation, and that everyone agree on the math and people just disagree about the interpretations. But interpretations contain statements that can be made mathematical. If you make any kind of statement that is formalizable about the theory you're discussing, that statement has to correspond to something in the theory. So often people will make claims about a mathematical theory that is absolutely not respected in the math, and you don't need to have knowledge about the world or knowledge about experiments to be able to refute these claims. All you need is to have knowledge of pure mathematics, and as soon as your interpretation makes statement within the theory, then you can attack it mathematically. That's how you go around that. And all these interpretations about quantum theory make a bunch of claims that are mathematic, that you can translate into mathematical statements. They might refer to objects within the theory, and as soon as they start to do this, that's where you can attack them.
Is one of those claims something like non-locality? Do certain interpretations, so-called, of quantum theory include a presumption that you can have these non-local signaling effects, faster than light signaling?
Yes, many people will make claims about non-locality that are fully mathematizable, and they will say things like locality mean that no action done in a system can have any effect on a system far away, and yet that's what they use with words. And as soon as you look at the math that they use to prove that claim, it doesn't even contain the statement. They add local hidden variables, but you should not say what I said before to talk about local hidden variables if these correspond to very different things mathematically. Your statement and the interpretation about local hidden variable doesn't correspond to this, so it's very bad logic.
You proved a theorem that I think was not necessarily explicitly about quantum theory, but rather was talking about how any physical theory that supports a no signaling theorem, it's got reversible dynamics, but it also has a local realistic formulation. Can you say anything further about that?
Oh, yes. The main idea of that theorem is that if we define no signaling and local realism in a way that is extremely close to the intuitive meaning or even isomorphic to it, to a bunch of very simple verbal statements like if I do an operation on a system A, it cannot have any effect on a system B, or if I have a system A and a system B, then the description of system A and B is nothing more than a function of the description of system A and system B. And if I have a composite system, I can separate it in the A and B. I can separate it into two descriptions of system A and system B, and all such statements that. So if you define locality, which is something that no one had done mathematically in a way that corresponded to the meaning of the terms before, and if you define non-signaling and you do a lot of math behind it, you end up with the fact that any theory which satisfies these extremely abstract and general principles, which include quantum theory, any theory that doesn't allow to transmit information. So to transmit information means that if I do something here, there's no observable effect there without some sort of interaction that take time to go there. Then it's because there was no effect at all, not just not an observable effect, but no effect at all. And what's interesting is that it gives an extremely wide and general theorem that go way beyond quantum theory, and that enables you to find out a very conceptual answer to the problem of locality in quantum theory, to answer the question of why is quantum theory local, or why does it have a local model? And the answer is because it is a non-signaling theory with well, the reversible dynamics is not fully necessary for you could extend the theorem somehow for some theories, but it's a very useful hypothesis. And so that's an example of something you can do with mathematics. With mathematics, if you define things with enough precision, you can prove very, very general truth. And that's something that's not often done in physics, sadly.
But in doing so, you can rule out some bad explanations sometimes in physics just using these mathematical techniques.
Yes. When I started quantum theory, I was told that quantum theory is non-local, but of course the arguments were terrible, didn't really correspond to anything in the maths. And if you create this model, it tells you precisely that in the many-world interpretation of quantum theories, all things work perfectly, and in all the other interpretations. Or many of them make the claim that no, it cannot be local. We've proven this, and blah blah blah, and that's very that's provably wrong.
Yeah, QED. All right, that's good. So some of this research you're doing under the umbrella, I suppose, perhaps you can tell me more, of the Conjecture Institute. Can you tell me a little bit about how Conjecture Institute has freed you up from what?
So I want to thank the Conjecture Institute for being the instrument of my freedom. I love you guys. Thank you, Logan. Thank you, David. Thank you, Aaron. And thank you to the founders and the donors. So the Conjecture Institute is an institute that truly believes in freedom and in the fact that all kind of knowledge creations require freedom. So in my case, I'm in a situation where I can do things for fun and only for fun, thanks to the Conjecture Institute. I no longer have to do anything I find boring. So it has freed me up from having to be a slave in the academic world. If I remained in the academic world, I would have a lot of difficulties. For instance, ideas like the manual interpretations are often not welcome for reasons I find very strange. It's like the academic world is full of very bad ideas in education, in economics, in physics, in sociology, and it reinforced these bad ideas through mechanism of pressure, and it's not even just that is a problem. Academics have to do things like give courses that I disagree with because they're fundamentally coercive. They have to do paperwork, they have to do all kind of things. So if you look at what an academic is doing in his day, it's a teeny portion of research and a lot of paperwork, a lot of course, and even the research. For me, it doesn't even count because it's not free research. It would be something if academics at least were able to do free research, but no, they have to comply to a lot of objectives, like your research has to be accepted by your peers who might or might not share your views, who whose reason to approve or not might have nothing to do with the validity of the argument. It's not a tradition of criticism in a free market of ideas. And because of this freedom, I can explore ideas that I want to explore, and I really enjoy exploring ideas without any kind of boundaries to solve problems that I care about. So if this week I was interested in the mathematical theorems about Hilbert spaces and permutation of bases and something technical. A few months ago, I was really into Stoicism, and the moment when David made the tweet, I was in a passionate discussion with him about interpretations of quantum theories and mathematical errors. So it's giving me the ability to explore ideas without boundary, without having to stress about any of the terrible constraints that destroy creativity. The Institute is enabling me to be an explorer of ideas, which is what I always wanted to be, and which unfortunately is not a job that is easy to find for people in the academia or anywhere else. As far as I know, it's one of the only places where such a thing can exist. And it's the only thing that can lead humanity to solve the most important problems.
That's a wonderful way to put it, as an explorer of ideas. I think this is something that is antagonistic to existing academic institutions, especially universities, where if someone wants to get funding, more often than not, they have to explain what the end point is going to be, what the goal is going to be. Not merely the problem they're working on, but the solution that they will actually get. And if they can't articulate this with great clarity, then they're not going to get the funding. The committee is not going to understand what they're going to do. And you can imagine a situation where you're in front of the committee saying, I want to explore this idea. They're not going to give you the money. They're going to give the money to someone who says they're going to solve some particular problem in some particular way. And I often regard many of these prescriptions that I hear from people working in certain areas of physics, especially physics that might be related to technology, is they are pulling the wool out of people's eyes by saying they're going to achieve this thing when they don't really have any better plan to achieve this thing. But they have to go through the motions to say it. If they want to be employed, they have to go through the ritual of explaining the supposed solution they're going to get to. But what you want a situation where a person can drop their problem. But if you're employed in academia to solve a particular problem and to publish papers, then if you don't do that, if you don't publish the papers regularly, if you don't make progress on that particular problem, if you drop your problem, you're a failure. But this is not the way that we should view things. We should view the academic or the intellectual as the explorer of ideas, as you say.
Yes, and I just want to point out that it's even worse. You have to say you will solve a problem, but it has to be a problem that other academics care about. And what you want to do is the opposite. For instance, about all jobs I see, they say we want someone who is going to work on non-locality and to prove some nonsensical thing. Of course, I'm not going to get that job. So it has to be, I'm going to make progress in an entrenched idea that, and pointing out criticism of it is not going to get you anywhere. So for me, it's already horrible. It's not even research. It's a bureaucratic masquerade where the goal is to produce a simulacrum of something that appears to be knowledge. And there's this pressure to publish paper, and part of the effect is that it doesn't have to be an idea that is correct. It has to be an idea that passed the reviewer's test, and it might contain mathematical errors as long as the reviewers were rushed to study the paper, don't see it, and as long as everyone keep their mouth shut, the ideas are going to pass. So yes, the alternative to this is to be an explorer of idea, not someone who's guaranteed to make progress in problems because there's no way to do it. Not even someone who work on a fixed problem because sometimes your interest might shift and you might be into something completely different. I started in math and I'm no longer doing math. As an explorer of ideas, I've changed what I'm doing, and if we're truly following our interest, then we have the possibility of at least truly engaging with the problem and of not having boundaries to what we're trying to solve. And anytime you put a boundary and a constraint, you destroy things a little bit.
Talking about boundaries and constraints, that would be something that is infecting the existing peer-reviewed journal. Respectable peer-reviewed journal articles are supposed to be the gold standard. But there are going to be a lot of hoops to jump through, a lot of hurdles to get over, just to get your paper into one of these respected peer-reviewed journals. Can you tell me about any experience you've had with that, or criticisms of that kind of system? How might that kind of system, which is held aloft as, this is the standard, this is the gold standard. If you want to actually produce knowledge, you need to first be published in Nature, or in our area, the physics journals around the world, the American Association of Physicists or something like that, or the Royal Society, whatever it happens to be. But what is the problem with demanding that something doesn't count as knowledge unless it has been published there?
The problem is very basic. It's that you're saying that some part of the universe, that knowledge is restricted to something produced by academics. And so this means that if you were a Greek philosopher, what you produced was not knowledge. If you existed in the year 800 years ago, where there was no journals, so everything produced before there was journal is not knowledge. So you cannot use any of these mathematical theorems. And how does it bootstrap itself into existence? Like you really, if you look at it at the fundamental level, you have a contradiction somewhere, that only some stuff. And is that a process that works? If so, why do they make papers with retraction and with a lot of errors? And so it's not a source that is infallible. It's a source that make error like any other source. And the alternative is to have a free market of ideas, is to say that it doesn't matter what is the source of the idea, whether someone has put a little stamp on it or not. It's just to evaluate the ideas for its own sake, and to say this is an idea that survived criticism, this is an idea I understand, this is an idea I accept because it fits my best understanding. And it doesn't matter whether someone else has put a stamp. And the problem of putting stamp, or so you ask about my experience. I can say that generally it's been fine, the fact that I tried to publish papers, but there was a case where the opposition to the paper was ideological, and that was very visible from the review. And that's not. It was not that any error was found. It was not that. It was just that what I'm saying has been disproven by everyone, so it cannot be true. But without giving anything that resembles an argument.
Someone else who has been vocal in criticizing the existing academic system and the existing journal publishing, article publishing system is Eric Weinstein. Now, Eric Weinstein goes a whole step further. He's also a mathematician who's taken interest in an area of physics and has developed a theory, geometric unity. But he goes one step further. At least he seems to imply in many of the interviews that he conducts about his own physics theory that there is a conspiracy, that there are people who are actively trying to suppress the production of knowledge. I don't know if you know much about his theory at all, but what do you think about this idea that there is a conspiracy? There are dark forces in the physics community actively trying to prevent people from coming up with new ideas.
So it's true that there might be people with some entrenched interest to some ideas, but it is not a total, in the sense that there might be a community that completely want to shut down your ideas, but it's not the whole world. So if it's the whole community that doesn't accept your ideas, there might be another reason at hand. So I've not lived that personally. What I've seen is, okay, one journal is biased against my ideas, but it's not the totality. And in the case of Eric Weinstein, I had a look at his paper and his lectures, and I can merely say that he doesn't try to be comprehensible. He doesn't try to be legible. He doesn't try to explain his theory to other experts. It's one thing if it would be one thing if a certain subset completely reject your ideas. It's another if no one accept them. Everyone, and that you just claim a conspiracy. The better and more productive alternative would be to make your ideas more and more explainable, to answer criticism. So these two things are different. One is to claim that some people might be against you, which might be the case, but the solution is often to make your ideas so clear and so unstoppable that anyone who would oppose them is forced to bow. And I want to point out, yeah, there's been case where there were dark force, if you will. When the theory of evolution was first proposed by Charles Darwin, there was opposition from many people, but that was never a total opposition, and there was never a way to fully prevent the ideas from seeping in, because powerful ideas eventually solve problems, and there's a point where there's just not a way for any force to stop them.
Yes, there's a wonderful YouTube series which the name of which escapes me at the moment, but it's basically a sequence of like 5 explainer videos all on the same topic. So it might be something like quantum physics as explained to a postgraduate, as explained to an undergraduate, as explained to a high school student, as explained to a 5-year-old, this kind of thing. I think this kind of thing might work for Eric Weinstein if he could do something like that, because I think the impulse that he has, from what I've heard, and I do not understand exactly what he's on about precisely in this geometric unity theory, but he seems to be pushing back against something quite reasonable, which is the quantization idea that the only way to get to a deeper understanding of gravity is to quantize it in some way. And he's reacting against that and saying, well, we can unify quantum theory and general relativity via another route. I think he's going via the route that quantum theory will be subsumed into general relativity rather than the other way around. But this obsession, I think, sometimes among certain physicists about unification leads them to get very territorial when it comes to their own particular theories. There's an interesting sociological effect there as well.
But you should not be territorial. I think your ideas should survive criticism. You should welcome any kind of opposition as long as it is reasoned, as long as it comes from good arguments. I think you should put your theory out there and make them public, make them as legible as possible, and then let people decide from themselves.
Yeah, I agree. Now, we've been going for an hour and 20 minutes. I could pull up the questions, but I don't think I will. I think we should wait. Yep, so I'll stop now.